Hello, everybody. I'm Andrei, and I work for JetBrains as a Senior Vice President of Investments, Research, and Education. Welcome to Regionals. Great things happen when great minds come together. JetBrains wants to seek out great minds all across the globe, support their initiatives, and work together to create great things that will make the world a better place. That's why JetBrains is proud to be a Global Tools sponsor of the ICPC. There are already many great minds working at JetBrains, and together we have created some amazing things, like the Kotlin programming language, for example. It keeps on growing and growing in popularity. In 2017, Google began officially supporting Kotlin as a language for writing Android applications. We have also created professional development tools like Cline for C++ programmers, IntelliJ IDEA for Java, PyCharm for Python, and also educational tools that help people learn and teach programming. The regionals are the biggest contest in the ICPC calendar. Thousands of talented people all over the world team up to solve complex real world challenges. These contests are the proving ground for future champions. But even if you don't make it through to the finals, the experience of competing in the regionals and the new friends you'll make along the way are priceless. Enjoy the ride. Best of luck to everyone.
Yeah, so the next problem is the cat, and there were no accepted solution during the contest. The pick here cat is Vichitra's cat, which was the inspiration for the story. And yeah, so the author is Kevin, and he will explain this solution.
Okay, thank you. So the cat is probably the hardest problem in this set, and I won't explain the problem, and I'll just go through the solution, or at least the main ideas of the solution, and not go through them in much detail, so that you have the opportunity to fill in the gaps yourself and attempt to solve it, because I think that will be very satisfying. All right, for this editorial or for this solution presentation, uh, we will use a straight arrow to mean an edge and a squiggly arrow to denote a path. So first thing is we want to characterize what exactly the decisive graphs are. So we want a simple criterion uh, that is equivalent to being decisive. So the first step is to start at an edge. And since the graph is decisive, there must be a path back from y to x. And together, they will form a directed cycle. So that's the first part of our graph, but that's not necessarily the whole graph. Okay, next slide. So the next step is to choose another edge. If the if the if this is not the whole graph yet, then there must be another outgoing edge. Let's say z to w. And since the graph is decisive, there must be again a path back from w to z. This path goes back to the cycle at some point, but where? There are multiple nodes in the cycle. I claim that it must return to z itself and not any other node. And the simple reason is if that's not the case, then there will be two paths between some pair of nodes. I think you can fill out the details. Anyway, so therefore, what happens is uh, the path returns back to z, and so we now have two cycles that has a single node in common, namely z. Okay, next slide. So we just repeat the argument until we get the whole graph. So while our current subgraph doesn't contain all the edges yet, just find another outgoing cycle, or I mean outgoing edge, and using exactly the same argument, you can show that it returns exactly at that node again. Therefore, from our current graph, we adjoin another cycle that has a single node in common. And we can do this until we get all the nodes of the graph. So therefore, we now know what a decisive graph looks like. It must consist of several directed cycles that are conjoined at points, and they form a tree-like structure. It's kind of like a cactus. So next slide, please. So here there is an example of a decisive graph, and it kind of looks like a cactus graph, except the edges are directed. So keep this in mind while you're trying to find properties of decisive graphs and solving the problem. This is what our graph should look like in the end. All right, next slide. So the next step is to solve the problem itself. We want to add edges so that our graph looks like this. So we first check the strongly connected components, because the strongly connected components, they must be of this form already, because there must be a path between every two nodes in a strongly connected component, and there must be exactly one path. So if we find an SCC and it doesn't satisfy this property, then we immediately output 0. And the condition can be checked in linear time. All right. So what about the remaining edges? The remaining edges will connect to different SCCs. Okay. So for the following, we will define the SCC graph as the graph where each SCC has been shrunk to a single node. Okay, next slide. So my claim is the remaining edges actually form a tree among the SCCs. In other words, if there are C strongly connected components, then there are exactly C minus 1 edges connecting different strongly connected components. Okay, so in other words, it looks like a tree, except it's not really a tree because the edges are directed. But if you ignore the directions, it will look like a tree. All right, next slide. So the proof is, I'll go through this quickly. If it's not a tree, then there will be a cycle, except this cycle is directed because each edge actually has a direction. However, the simple cycle will not be an actual cycle because we assume that the cycle goes through nodes from different SCCs. However, in a decisive graph, that's impossible. If you remember our earlier picture, there are no cycles there that are not directed cycles. You cannot find a simple cycle if you ignore the direction that is not a directed cycle in the original graph. So that's basically the proof. So next slide, please. So we now know that among those edges, there are no cycles. Therefore, they form a forest on the original nodes. They only form a tree among the SCCs, but remember that we shrunk the SCCs earlier. If we unshrink those SCCs, then the C minus 1 edges will form a forest among those nodes. Okay, we now need to add edges, additional edges, so that the whole thing becomes decisive. And we now know that the remaining edges form a forest. Okay, next slide. So the next observation is the additional edges we add must connect nodes from the same tree of this forest. In other words, if you look at the non-SEC edges, then we should never add an edge that connects two different trees. So why is that? I won't give the proof here, but the insight is essentially the same as in the previous proof, which is you cannot find a cycle that is not a directed cycle originally. So the proof is quite simple once you get familiar with decisive graphs. But after knowing that, that actually makes our lives simpler, because that means we can solve for each tree separately. We find the number of ways to turn each tree into a decisive graph, and then we just multiply all those answers together. Therefore, finally, we have simplified our problem so much that what we're left with is a tree. All right, next slide, please. And this is the final part of the solution. And I think I won't actually give the answer here, because if you were able to follow up to this point, I think you can fill in the details of this remaining part. This is, I think, one of the easier parts of the problem. I just leave hints here. So the first hint is choices can be made per node. What the choices are, I won't elaborate here, but when you're trying to turn the graph decisive, you will eventually discover that you will have to make certain choices per node, and you will and my claim here is that you can make those choices independently of other nodes. The second hint is the choices in a node is bears a striking resemblance to matching. Okay, after doing all of those, I just mentioned here that the final solution will run in linear time, and that's the solution. I hope you enjoyed it.